This comes out of section 1.7, infinite series. We're going to do something a little bit different in this example than the previous two, and talk about repeating decimals. 0.333333333. Most of you already know that this equals a third, but I want to show you a way of being able to find out what a repeating decimal equals. It does equal, 0.3 plus 0.03 plus 0.003, etc. So another way of looking at this is that it's a sum, a geometric series. 3/10 plus 3 over 100 plus 3 over 1,000 plus ... So because it has a common ratio of a tenth, it's multiplying by 1/10 every time, because the terms, if you divide one by the previous, you get 1/10. You can say, well, what would be the infinite sum of this? It would be the first term divided by 1 minus the ratio, so it's going to be 3 over 10 divided by 1 minus 1 over 10. 3 over 10 divided by 9 over 10 equals 3 over 10 times 10 over 9, 3 over 9, which reduces to a third. Now, in this case, you already knew a third, so it seems like a waste of time, but what if we have a second example here? If I'm asked to express 1.35 repeating as a fraction. Now, this one's a little bit different because the 1 and the 3 aren't repeating, so I have these extra digits up front. Maybe you can leave them up front as, that's 13 over 10. But then I have 5 over 100 plus 5 over 1,000 plus 5 over 10,000, etc. And this part, turns into a geometric sum again. So let's ignore the 13 over 10 for a second, but not forget that it exists, and say, well, what's the infinite sum of what I've got in the brackets there? So it's going to be the first term divided by 1 minus the ratio, so 5 over 100 divided by 1 minus 1/10. So this will be 5 over 100 divided by 9/10. So we've got 5 over 100 times 10 over 9. Things reduce a little bit, and I end up with 5 over 90. That does reduce, but let's not forget what we're looking at. Now, the 5 over 90 just means that that's 0.05555555. That doesn't include the 1.3 we had in the first question. So we still need to say, what's 13 over 10 plus 5 over 90? I find a common denominator, maybe say that this is 9 times 13, 117 over 90 plus 5 over 90 equals 122 over 90. Worthwhile checking with your calculator to see that you didn't screw up, and it should give you 1.355555555. You can still reduce this answer a little bit. I can see that it's even on the top and the bottom, so divide top by 2, divide the bottom by 2, and 61 over 45 looks like it's about as good as I'm going to get. 61 isn't divisible by too much, so I've got an answer. Again, check it with the calculator. It equals 1.355555555. Now the last one I want to do is maybe slightly trickier. Instructions are the same, but we've got 5.2 and then 134, 134, 134, 134. So I've got 5.2 plus 134 over 10,000 plus 134 over a million. I have to add three zeros because I'm adding 3 decimal places each time. 134 over plus. So again, the geometric series part is the part in the brackets. Later I can add 5.2 or 52 over 10 or whatever I want to deal with. But the infinite sum of what's in the brackets is a over 1 minus r, so it's 134 over 10,000 divided by 1 minus, the common ratio here is 1 over 1,000. 3 digits are repeating. I needed 3 extra decimal places when I went to the next term here. So I've got 134 over 10,000 divided by 999 over 1,000. 1,000. So it ends up giving me 134 over 10,000 times 1,000 over 999. Good news is a lot of these zeros cancel out, and I basically have 134 over 9990. So a little bit of an ugly number here, but 134 over 9990, and you can try that by itself on the calculator, and you'll see that it does equal 0.0134134134. So you've got the right, number of repeating digits here. We still do need to add that to 5.2 or to 52 over 10. Find a common denominator, etc. But hopefully that part is becoming old news to you now. And you'll get, not a particularly pretty number, but once you reduce it, 26041 over 4995. It originally starts off being over 9990, but the top and the bottom are even. Divide them both by 2, and you get this. Some people prefer to have them mixed, and they end up with 5 and 1,066 over 4995. Really, the idea here is that you understand the relationship between the geometric series sum, infinite sum, and how you can turn it into a fraction, not so much whether you've got a mixed fraction or an improper fraction at the end.